everybody. Today we're going to be talking about chemical reactions in terms of the energy, both the energy they need to react and the energy that they either absorb or release in the process. So when we're looking at one of these potential energy diagrams, just like this one, we are talking about characterizing the energy of the reactants starting on the left-hand side where it is starting at the 50 kilojoules mark, and then ending on the product side, on the right-hand side, at the 100 kilojoules mark. PE stands for potential energy. Reaction pathway is referring to the progress of the reaction from the reactants to the products. All right. Some reactions occur spontaneously, but some reactions need a boost. And so the ones that need a boost are the ones that need to have some activation energy. So an activation energy on the graph is represented by that hump you see that connects between the reactants and the products. The hump might be the highest amount of energy involved, or it might be some middling amount. In this case, the activation energy is much higher than the energy of the reactants and quite a bit higher than the energy of the products. So this is still a potential energy diagram. The course of the reaction is other terminology that means the same thing as the pathway of the reaction. All right, energy of reactions. In every chemical reaction, there is either going to be an absorption or a release of energy. And you can tell by looking at the graph if there is an absorption or a release of energy when you look at the difference in energy between reactants and products. The second bullet is really important that you make sure you get written down in your notes. Here, it is describing energy as needing to be absorbed when bonds are broken. Bonds do not spontaneously break on their own. They need to absorb some energy to break the bonds, and then some energy is retained in the remaking of the bonds. It is the difference between the products and the reactants that are going to give us the overall idea of the overall energy change, where in one case, the products might have a lesser potential energy than the reactants, meaning we have an exothermic reaction because heat has been released as energy, or we would have the products having greater potential energy than the reactants, so heat has been absorbed, and thus an exothermic reaction. When we are talking about the amount of energy absorbed or lost as heat, we are going to need to subtract the heat of the products minus the heat of the reactants. In simple terms, this is truly just a subtraction problem. So in the case of this example here, we have reactants beginning on the left-hand side, and we have products ending on the right-hand side. Our reactants are at a potential energy of 50 kilojoules, but our products are at a potential energy of 100 kilojoules. So if we were to subtract products, 100 kilojoules, minus reactants, 50 kilojoules, we'd end up with an overall gain of energy for the reaction of 50 kilojoules. And so we would know, because there has been an absorption or gain of energy, we would also know that in fact what we have is an endothermic reaction. Now you see that hump in the middle. That hump in the middle, the difference between the highest peak and where the reactant started is going to represent your activation energy. In this case, the size or the amplitude of the activation energy is about 200 kilojoules, which is not the same as the total amount of heat energy that is absorbed. As you can see, that is only 50 kilojoules. All right, so let's talk about the parts of the endothermic reaction graph. And you are going to have to be able to identify an endothermic reactions graph. So this is where energy of the products ends up greater than the energy of the reactants. Heat gets absorbed, as you already know from last class period. Temperature of the surroundings decreases. And delta H, or the difference between the products and the reactants, is a positive number. I'll say that one again. Delta H, which is the difference between the products minus the reactants, is a positive number. Everything on this screen you need to add to your notes. Same thing for the exothermic reaction. All of this needs to be added to your notes. In this case, the reaction proceeds, but there is a loss of energy. In fact, the energy of the products is less than that of the reactants. Heat has to be released for this to occur, and overall the temperature increases for the surroundings. But when we describe the heat energy change, we say that it's negative because the potential energy of the products is less than the potential energy of the reactants. And when you subtract them, you'll end up with a negative number. When we talk about this delta H, or the change in heat energy, we are talking about the heat of formation of the products. Every compound, as the product, has a heat of formation. Elements, however, do not have a heat of formation because they were not formed. They are simply existing in nature. Since energy is released when bonds are formed, these values are usually negative. So usually you are going to have a negative delta H or an exothermic reaction. So once again, this equation becomes very important for you. To find the overall enthalpy of a reaction, we are going to use the formula delta H of the entire reaction is equal to that of the products minus the delta H of the reactants. So in this example, we have to figure out if this reaction is endothermic or exothermic. And so we are going to have to compare what we have going on here. And remember, we're going to use products minus reactants. But we also have a balanced equation, and we are going to have to pay attention to the coefficients in the balanced equation. But if you look at our data table here, we have a heat of formation for methane, which is this value right here. We have a heat of formation for water, which is this value right here. And we have a heat of formation for the carbon dioxide, which is this value right here. But we do not have a heat of formation for the oxygen, and that is because the heat of formation for an element is 0, so we don't need to use it. We're still going to use products minus reactants, so we're going to find our heat of the reaction by taking the heat of formation of our products multiplied by their coefficients. So let's get started. We have carbon dioxide's heat of formation, which is negative 393.2. And we're going to add that to that for the water because it is also a product. And you know, as you can see by the coefficient, that water, there is 2 of them. So we're going to multiply it by negative 285.8. Now, we have just found out the heat of the products. Now we're going to subtract the heat of the reactants, and we only have one reactant with a value, and that is methane, and it does not have a coefficient in front of it, so we are just going to subtract the negative 75.8 kilojoules per mole. And when we do this math, we will come out with a negative 889 kilojoules. Now, remember what we said. We were calculating delta H. And when we made our foldable, we said, and in the previous slides, we said that delta H, if it's negative, is exothermic. So we have an exothermic reaction, and that makes perfect sense because this reaction is a combustion reaction, and most combustion reactions are exothermic. That is the end of your notes for today. If you have anything that needs to be made up at this time, please go take care of making up your assignments. This has been your notes. Please re-watch this if you need to get the rest of your notes down. I will expect a file upload by you to show me the notes that you wrote. Thank you very much, and bye-bye.